Okay, so you're able to see a screen.
Yes, sir.
Yes, sir.
Okay. So we'll looked at all these topics. Okay, that is how the offsprings are made by chopping the bit strings, and you have to swap the tails. And how mutation is done by randomly choosing a bit with a random number R, and then you change the sign of the bit. That is 0 is changed to 1 and all these things. Okay, so now the thing is that later on people found that there's no need to convert to the decimal numbers to binary, then cut to the strings and swap the tails, and then again reconvert them to real numbers. So people found that you can have continuous or floating point or decimal genetic algorithm without any need for binary numbers. So here the numbers are represented in the usual way, just by decimal notation. So what will we do in this continuous and floating point GA, and how is it different from binary GA? So what you do is that, so here also you take a random number of x coordinates, so x1, x2, x3 up to x10. So this is the x coordinate values as it is. So it is not converted to bit strings like this. Okay, there's no need to do all these things. So it is just written in the decimal notation as is the usual, and you also note the objective function value. Okay, fitness. So in this case, okay, so this is the best, this is next best, this is next best, and this is the least. Okay, so it has to be ranked later. Okay, okay, so now let us take two parents, say x1 and x3. These are two best parents in the list. How do you do the crossover or the mating between them? Okay, without using the binary numbers. So what is done is that you do interpolation, the algebraic interpolation between the two numbers. So offspring 1 and offspring 2 are obtained. What you do is that you have to generate a random number beta between 0 and 1. And okay, the offspring 1 is obtained by beta into x1 plus 1 minus beta into x3. And offspring 2 is obtained by 1 minus beta into x1 plus beta into x3. Okay, so suppose two parents are there, x1, x3, and suppose beta is equal to 0.2. Okay, okay, so one offspring will be here at a distance of 20% from x1, and another offspring will be here at a distance of 20% from x3. But both the offsprings will be inside x1 and x3. It will not be outside. Okay, you won't get outside. So if you do this method of interpolation, you can get some two offspring, just like you get. Okay, so this one x1 apostrophe, x2 apostrophe. You get two children inside x1 and x2. So this is found to be as good as doing the chopping up of the binary strings. Okay, then mutation in floating point genetic algorithm. So out of a population of 10, decide how many members n to mutate. Okay, so the probability of mutation is n by 10. So in some GA subroutines, you have to give the probability of mutation, and it will do the rest by itself. So what is the practical method to do mutation in floating point genetic algorithm? So suppose I have 10 population of 10, x1, x2, x3, x5, sorry, x4 up to x10. Okay, so what I do is that I generate a random number between 1 and 10. So suppose r equal to 4. Okay, then x4 I take. I remove this x4 from the population and replace it by another newly selected member from the same branch. So I remove this x4 and I replace it x4 apostrophe, which is a new member which will replace x4. So this is how mutation is done in the floating point genetic algorithm. So it is very simple if you use the floating point or decimal genetic algorithm, because whatever thing is done by the binary genetic algorithm, the equivalent operations are available in the decimal genetic algorithm. Then for, okay, now we'll see for both binary and continuous genetic algorithm, first generation. Okay, first generation are made up of the first 10 x values. Okay, so first generation is like this: x1, x2, x3, x4, x5, x6 up to x10. Okay, and the portion, say half, are rejected, and this remaining 5 are crossed over to give another 10 offsprings. Okay, another 10 offsprings. Okay, so so what you can do is that, so various methods are, so this is the first generation. So various methods are there to produce the second generation. So one method is that with this 5 parents we can produce 4 children. I mean eight children. X1 apostrophe, X2 apostrophe, X3 apostrophe, up to X8 apostrophe. 8 children are made, and then the remaining 2 population are left. Okay, we need 10. So what you do, 2 of these parents can be inserted here, X4, X5. Okay, so because we want to have some genes of the good parents also. So this is one option. That is, you partially fill the next generation with the offspring, and the remaining gap you fill with some good parents like this. And another option is that you completely fill the next generation with new offsprings. Okay, X5 apostrophe, X6 apostrophe, up to X10 apostrophe. All are new offspring from this 5 parents. So that is also another strategy. So various type of different methods are there. And since this is not based on mathematical logic, it is difficult to say if this is better than this. Okay. These are all heuristic or rule of thumb methods. Okay, so okay, the offsprings, second generation, offsprings of the first generation, say 8 offsprings plus 2 parents can be used to give the next generation of 10. Okay, so then the second generation will also undergo crossover and mutation to give third generation. So it will go on like that. So as the generations continue, all members of the population will converge to the global optima. So it is like this. Okay. So all the finally after 100 iterations or so, all the 10 members will coincide here. It is x1, x2, x3 up to x10. All will be bunched up in the global minima after say hundreds of iterations. Then at that time you can stop the iterations. Okay, then so this is important. It will be asked for exam. That is, you have to generate a sample population and show these operations. Okay, some schemes for parent selection, crossover, and mutation. So the roulette-wheel method is the popular method to choose the parents for mating. Okay, so here the probability of a parent being selected for crossover is proportional to its fitness. So I will explain what is the reason for this. So, okay, now suppose I have population of 10, x1, x2, x3, x4, x5, x6, x7 up to x10. So I reject this worst. Okay. So now 5 parents are there. So you can do the crossover between them with 2 parents at the time, x1 and x2, then x3 and x4, then x1 and x3, then x4 and x3, etc. But here the highly important thing is that these 5 parents are having some variation in the fitness. Maybe x1 has best fitness and x5 has the worst fitness among these 5 parents. Of course, the fitness of x5 will be far better than these rejected ones. Okay, but what I am saying is that inside this parents itself, there is a relative difference in the fitness, and you should show some priority to good parents like X1 and X2 and less priority to bad parents like X4 and X5. So that is done by this roulette-wheel method. So how the roulette-wheel method we'll study in this class. Okay, suppose population is 10, n is equal to 10 and small n is equal to 5 is the pool of the fittest members. Okay, so 5, small n equal to 5 is the pool of the fittest members. In this method, first all the fitnesses of the parents have to be normalized to positive scale to avoid negative probabilities. So what is that we'll see in the next slide. So what they are saying is that suppose f of x is equal to minus 5, f of x is equal to minus 25. These negative numbers should be avoided and they should be converted to positive numbers before you do this roulette wheel. Okay. Okay, so out of these 5 parents in the pool of 5, the probability of selecting the ith parent is given by fitness of that parent, fitness of that ith parent divided by sum of the fitness of all the 5 parents. Okay, so that is the relative probability of picking that of picking the ith parent. So f of xi, fitness of the ith parent divided by sum of fitness of all the 5 parents. Then there's something called cumulative probability. So what is it? We'll see later. Okay. So cumulative probability is nothing but the successive sum of this pi. Okay. So we look at this with a simple example. Okay, so this type of question we asked for exam, okay, for the end semester exam. Think, or even for the second assignment. That is, you will be given some dummy population and you have to show how you are doing the ranking, crossover operations and all with one example each. Okay, so let us look here. Illustration of a single variable objective problem, maximize f of x. So it is only x versus f of x. There is single variable problem. Okay, so it is like this, x, fx. So first I select 10 random values, x1, x2, x3, x4, x5, x6. Okay, so and I note the f of x values for all these things. And those f of x values are written here. So x1 is equal to 1. X coordinate is 1.0. So okay. So x coordinate is 1.0. The f of x is minus 10. Okay. So you can see this is the abnormal value. Okay. Then x2 is like 0.6 and f of x is 3. Okay. So 10 values of x which are randomly picked up from the x coordinates and corresponding fx values are written here. So here first you have to eliminate this negative number. Okay. So what is done is that you add plus 10 to all numbers. Plus 10. Okay. So now this has become 0, 13, 15, 24, etc. So this has been reduced to 0. All the other objective functions have been added by plus 10. So there is no discrimination. Okay. Plus 10 has been added to all other objective function values. So it is the same relative difference in the objective function values. This is the first step. Okay, then you have to rank them. Out of this, x4 is on top because it's the highest value of objective function. Next is x6, 23. Next is x5, 22. Okay, so it is ranked like this. Obviously, the worst is the 0 value at the bottom. Okay. Worst 50% is rejected. Okay, the first 1, 2, 3, 4, 5. And the first 50% is accepted as parents. Okay, so this 50% is called crossover pool. of 50% or crossover rate of 50%. So this is the terminology used, crossover pool or crossover rate. So some algorithms will take 60% and reject the 40%. And some algorithms will take 40% of the parents and reject 60%. And some algorithms will take 50%, 50%. So various combinations are there. So because it's not mathematical method, you cannot tell in advance which will give good results. Okay, it is all rule of thumb. But roughly it varies between 40 to 60. That is the crossover pool. Okay, so now we need to concentrate only on this. Okay, so these are the 5 parents who have been shortlisted in the last slide. This is the best, next best, third best, fourth best, fifth best. This is the normalized fitnesses. So now you know why the fitness is converted to positive values. Okay, suppose this is minus 21. Then all the calculations will go wrong. Okay, so suppose this is minus 23 and minus 21. Then now this entire method will not work. So all the fitnesses have to be converted to positive value. So this is actually sigma f of x I. I is equal to 1 to 5. Okay. I is equal to 1, I is equal to 2, I is equal to 3, I is equal to 4, I is equal to 5. Okay. Okay, so sum of all the fitnesses 107. Okay, so probability of selecting x4 is 24 by 107. Probability of selecting x6 is 23 by 107. This is 22 by 107, 21 by 107, 17 by 107. So these are expressed as the fraction. So if you do like that, you can see that highest probability of selection is given to the topmost parent. Then the next slightly less probability of selection is given to second one, and the lowest probability of selection, that is 15%, is given to fifth parent. Okay. So next, all these things have to be written in cumulative probability scale. That is, you successively add this p-value. Okay, so first column is say 0.2243. So this is actually this second probability plus the previous value. That is 0.21495 plus 0.22430. That is this one. Then this one is this pi plus the previous two values. Plus the previous two values of pi. So finally, this will become 1.0 because this is the sum of all these PIs. Okay. So cumulative probability will become 1. Okay. So what is the purpose of finding cumulative probability? So this is highly important for randomly selecting two parents based on some consideration of their relative fitness. So what we can do is that this cumulative fitness QI can be represented in this scale. Okay. Right, please. Okay. It can be represented in this linear scale. Okay. So here you can see that X4 is having the largest space, that is from 0 to 22.43. Okay. And X6 is having a smaller slot. This you can call it slot. Like in the roulette wheel machine, slots are there. This is the slot. Each parent has a slot. The X7 is the worst parent. It has a smallest slot. And X4, the best parent, has the largest slot. So you may be aware of roulette wheel type of gambling in the the casinos and all that. So roulette wheel will look like this. It is a wheel with different sectors. Okay, each sector will have a color, like, red, green, blue, yellow, etc. So this roulette wheel will be rotating and you have to throw a ball. Okay. So if the ball falls in this sector, it will have certain number of points. If the ball falls in this blue sector, it will have a different number of points. And if the ball falls in this sector, it will have another different number of points for the gambling. So same thing is done here. So where is the ball here? Huh? The ball is actually a random number which we generate. So suppose we want to select two parents for a crossover. Okay. So this is our roulette wheel, or we can call it roulette slide. Okay. So select one parent by generating a random number R between 0 and 1. Suppose R is 0.53. So you can assume R is a roulette wheel ball. So R is 0.53. So that ball will fall in this slot, X5 slot, because 0.53 is somewhere here. Okay. This is 0.53. So this is 0.439. This is 0.64485. So it will fall in the slot of X5. So this parent is selected. So then we need to select one more parent. Okay. So generate another random number. Suppose R is 0.1343. So that will fall in this slot. That ball will fall in this slot. 0.134. So that is in the slot of X4 slot. So the second parent is X4. First parent is X5. So we can see that parents which have the larger length of the slot are likely to get more random numbers to fall within that range. And parents which have shorter length of the slot are likely to get less random numbers to fall in that slot. So this automatically gives importance to high fitness parents like X4. It automatically gives less importance to low fitness parents like X7. But the beauty of this arrangement is that X7 is not totally avoided. Okay. Once in a while, X7 will get selected, and so it's not being unfair to that. Okay. So this is the roulette wheel selection. Okay. So two parents are selected, X4 and X3, and if you do the interpolation between them, you get two offspring, X4 apostrophe, X3 apostrophe. Okay. So now we have to specify how many crossover operations we want. That is n cross. So you can see that the number of offspring is equal to each crossover operation into 2. So that must not exceed the population size. So our population size is 10. So we can have only 10 offspring. Okay. So we can have only 5 crossover operations. 5 crossover operations will give 10 offspring. So you have to stop with 5 crossover operations. So that is the maximum. So another option is that you can have 4 crossover operations, which will give 8 offspring. Okay. Then remaining 2 is taken from a previous parent. Okay. So this is also another scheme. Okay. But usually the first one is used everywhere. That is, the entire next population is filled with offspring. Okay. So these two are explained here. Okay. We can have 4 crossover operations. That is 8 offspring which will go to next generation. Then the remaining 2 will have to be picked from the 5 parents by roulette wheel. Okay, then it's not over yet. Okay, so this is the 5 good parents. You got 10 offspring. Okay, so then you need to do mutation here. Okay, so what you have just done now is crossover. Okay, so mutation is separate. So what you have to do is that you have to randomly pick one member from the new generation. You have to remove it and you have to replace it with a new number selected within the search array. So that is called mutation. And why mutation is done is that hopefully it will give better result than, hopefully this mutation will improve the result. Okay, so this is the thing. So in the exam, you will be given one starting population like this. Okay. Okay, now one starting population like this will be given for exam, and you have to show how it is normalized, how the parents are shortlisted, and you have to show one or two sample crossover operations. Obviously, you cannot do 5 crossover operations because time is not there, but one or two sample crossover operations, and also you have to illustrate how a mutation operation is done. Okay, then some other schemes for parent selection. Okay, so we studied roulette wheel, which is actually the best type which is used everywhere. Some other lesser known type of parent selection is a random pair. A random parent means all 5 parents are assumed to be equally good, although their fitness is relatively different. So from the best 5 parents, 2 are picked at random with equal probability. Basically, you select a random number between 1 and 5, and accordingly you pick the parents. So if r equal to 1, the first parent is 1. R equal to 3, the next parent is x3. So this is the random pairing. So this gives equal importance to all parents without any consideration of their fitness. So it is not used much. Okay, then this elitism is a highly important concept. Okay, elitism is a scheme whereby the top ranked parents of a generation are guaranteed to be selected for crossover or deliberately inserted into the next generation. Elitism. So elitism sounds very good. Okay, that is, you pick the best parent of one generation and insert it into the next generation, thinking that the good genes will be carried over. But the danger is that what appears to be the best parent in one generation may be only a local maximum. There may be better maxima somewhere else. So it is not good to jump into conclusions like deliberately picking what appears to be a good parent and inserting into next generation. So then the search may go to a particular local maxima where that parent occurs. Okay, so the important thing is that uh, elitism versus diversity. These are two opposing forces in a genetic algorithm. And not only in genetic algorithm, in all heuristic algorithms like simulated annealing and particle sum optimization, these same concepts work. So what is the meaning of elitism versus diversity? Diversity means encouraging the selection of diverse members across the entire variable range. So random operations like roulette wheel mutation encourages diversity. So it prevents genetic algorithm from being stuck in a local outcome. So why are we doing this mutation and roulette wheel search and all these things? Because this will allow us to search the search space more in a diverse manner. Okay. So you won't get trapped into a local maxima or local minimum. But on the other hand, elitism means showing preference to a top ranked member in the population. In some cases, it can lead to quick convergence. That is by luck. Some cases, by luck, it can lead to quick convergence because that particular highly ranked member may be coming from the global optimum. Okay, but if it is not like that, you will get stuck in some local optimum. Okay, so these things and all can be asked as theory questions. Okay, what is elitism versus diversity in genetical? Now, not only in genetical, particle sum also, we can do the same things. We can pick the best population from one generation and deliberately insert it into another generation. Okay. So we can stop now here. Okay, we'll take attendance.